Hey everyone, welcome back to the channel. Today we are going to build a deep learning project using PyTorch that can recognize handwritten digits. We will not only train an artificial neural network on MNIST dataset, but also create an interactive digit recognition app using Pygame. So by the end of this video, you will be able to draw a digit on the screen and have a model predict what number it is. Now, you might be wondering why we are using artificial neural network instead of convolutional neural network. Well, since MNIST images are small and simple, only 28 cross 28 pixels, and ANN is good to classify them. But for more complex datasets like real world images with higher resolutions, CNNs perform much better. I'll be creating a future videos where we will build a CNN model for more advanced image recognition task. So stay tuned for that. So let's get started. So before we dive into the code, let's break down what we are building. So in part one, we'll train an artificial neural network on MNIST dataset. MNIST stands for Modified National Institute of Standards and Technology. It is a famous dataset for handwritten digits, that is 0 to 9, commonly used for training and testing machine learning models in image classification tasks. So why is MNIST popular? Well, there are a few reasons, like images are small and simple. That is, each image is size of 28 cross 28. Images are in grayscale. So it has 60,000 training images and 10,000 test images. Okay. Many deep learning models are evaluated on MNIST. Okay. And it is good for beginners. So we are also using that. Okay. So we'll create a simple ANN using PyTorch, train it to classify handwritten digits from 0 to 9, evaluate its accuracy on the test set. So like I said, it has 60,000 training images, and in test set, it has 10,000 images. Okay. Then in part two, we will build an interactive digit recognition app. So use Pygame to let user draw a digit on the screen, convert the image into format the ANN understands, use our trained model to make predictions in the real time. Okay. Now let's break it down to simple and smaller steps. So in step one, we'll import the libraries. Step two, we'll build the artificial neural network. Step three, we'll load the MNIST dataset. In step four, we'll train the model. Step five, evaluate the model. Then in step six, we'll build the interactive Pygame where we'll draw the digit, process the drawing, and make predictions. Okay, so let's get started. So I've created a new project, Handwritten Digits App AI. I'm using PyCharm as an editor. You're free to use any other editor you would like to. So let's create a new file here. Let's call it as digits.py. So let's start with the step one, that is importing libraries. Okay, so import torch. So first let's install the torch library. So pip install torch. Now let's have few more imports. So import torch.nn. NN stands for neural network. Let's install a few more libraries. So install NumPy. Let's install Pygame. So we have import torch, torch.nn and torch.optim. So NN stands for neural network and optim is optimizer. So these are PyTorch core libraries for building and training the ANN. Then we have torchvision and torchvision transforms. So these are used to load and pre-process the MNIST dataset. Okay. Then we have a data loader. It helps load data in batches for training and testing. Okay. Then we have a Pygame. It is used to create an interactive window for drawing digits. Then NumPy helps with the numerical computations, and OpenCV used to process the draw image before passing it to the neural network or model. Okay, so let's clear the screen. So now we are done with the step one, that is importing libraries. Now in step two, we'll build the artificial neural network class. So let's do that. So we'll have class, let's call it as ANN, and it will inherit from ann.module. Okay, so let's understand this. So imagine this is the image, okay, and this image is 7 pixel by 7 pixel. Okay, so we have total 49 pixels, and since it's a grayscale image, the RGB values would be either around 0 or around 255. Okay, so here we can see that all the pixels are 0 except these pixels. Okay, so if we draw that, that becomes the number 7. So this image will be our input. Okay, so we'll pass it to the input layer. So first we flatten the image. That means we convert the image into one-dimensional vector. Okay, so for example, let's say image is 0 to 55, 0, 0. Okay, once we flatten it, it would become 0 to 55, 0 and 0. Okay, so once we flatten this image and pass it to the input layer, we'll have 49 neurons in the input layer. Okay, then the hidden layers, we'll have two hidden layers. Each layer will have 128 neurons. Okay, and in the output layer, we'll have 10 neurons because our output will be between 0 and 9. So we are predicting digits between 0 and 9. So our output will have 10 neurons. So let's implement it. So first we'll have the constructor and we'll call the superconstructor. So we'll have total 4 fully connected layers, one for input, one for output, and two for hidden layers. So let's have first fully connected layer, call it as FC1 and then dot linear, and size would be here. The image size is 7 by 7, so we have 49. In our case, the image size is 28 cross 28, so that would be the size of input layer, and the output would be 128. Okay, now the second fully connected layer, 128 input and 128 output. Then the third fully connected layer, call it as FC3, again 128, 128, and the last fully connected layer for the output. So this would be an n dot linear and 128 input and 10 output. Okay, then we'll have the activation function, rectified linear unit, RLU, and n dot. Okay, now let's define the forward method. So this defines how input moves through the network. So input X. So first we will flatten the image. So -1, 28 cross 28. So this flattens the image into one-dimensional vector. Then we'll pass it to first fully connected layer, X, and then we'll apply the activation function. Okay, so X. We'll do the same thing for fully connected layer 2 and fully connected layer 3. And then for the output layer, we'll not apply the activation function. We'll just have FC4 and return X. So again, first we flatten the image. Okay, so convert the image into one-dimensional vector, then pass it to fully connected layer 1, apply the activation function. So this activation function helps introduce non-linearity, allowing the network to learn complex patterns. Okay, And then same thing for fully connected layer 2, 3, and then 4, and then we'll return. Okay. So we have created a separate video on artificial neural network where we have discussed that in detail. I'll leave the link in the description. Please visit. Okay. And now with that, we are done with the step 2. We have built the artificial neural network. Now in step 3, we will load the MNIST dataset and apply necessary transformations. Okay. So So let's understand this. So the transform variable is used to pre-process the MNIST dataset images before they are fed into the neural network. Okay. Okay. This transformation pipeline ensures that images are in the right format and scale for training the model efficiently. Okay. So we use toTensor function to convert image to tensor. It converts the PIL image or NumPy array to PyTorch tensor. And why do we need it? PyTorch model requires input data in the form of tensors. Okay. So as we have seen earlier, the pixel values are between 0 and 225. So this method converts the image pixel values from 0 to 225 integer to 0 to 1 float value. Okay. It also changes the shape from height, width, and height, width channels to channel height, width. Okay. So the channel is nothing but RBG, and this is the height and width of the image. Okay. And this is the PyTorch format. Okay. Let's clear the screen. Now next, the normalize method. It normalizes the pixel values. Okay. So what it does, normalize pixel values to the range of -1 to 1. And why it is needed? Normalization improves training stability and help gradients flow better. Okay. So many activation functions like ReLU or 10H work better when input values are near 0. So we take the mean as 0.05 and standard deviation as 0.05. Okay. So this converts the original pixel values, which are between 0 and 1 after the tensor, into -1 to 1. Okay. So this is the example calculation. So if original pixel value is 0, it will be converted to -1. If original pixel value is 1, it will be converted to 1. And if it is 0.05, it will be converted to 0. Okay. So without normalizations, the values are between 0 and 1. And with normalizations, the values are between -1 and 1. Okay. So let's clear the screen. Now let's have the images from MNIST dataset. So we have two sets, one for training and one for testing. Okay, so these are the images downloaded from MNIST datasets. Okay, so we'll download it to this location, and download is true, and this is the transform variable. And for training set, the train will be true, and for test set, it would be false. Okay, then we'll have the data loader to fetch the data in batches. The batch size is 64 here. And for training, the shuffle is true. And for testing, the shuffle is false. Okay. And now we are done with the step 3, loading the MNIST dataset. Okay. Next, we will train the model. So, so let's initialize the model. So ANN. Now let's have the loss function, and we will use cross entropy loss function. Okay. So cross entropy loss function is a standard loss function for the multi-class classification. Okay. Now we'll have the optimizer. So we'll use Atom optimizer, model.parameters, and let's have the learning rate as 0.001. Okay. Now let's train the model. So train the model. Okay. So we'll have number of episodes as 10. So we'll start. So at the start of each episode, we'll set the loss to 0.0. Now let's get the images and labels in train loader. Okay. So remember, train loader has the set of images for the training purpose. Okay. So first we will reset the gradients. Okay. Now let's feed these images to the model using forward pass. So we'll call model and we'll pass the images. Okay. And we'll get the outputs. So these are the predictions. Next, we will compute the loss using the loss function, and we'll pass outputs and labels. Okay. So these are the actual labels and these are the predicted labels in the output. And we'll pass it to the loss function to calculate the loss. Now we will back propagate the loss. So backward and update the weights. So call the step function. And now let's add the loss to this loss. Okay, let's change the name. Let's call it as running loss. Okay, so we'll update the running loss to loss dot item. So after each episode, we will print we'll print the episode number and the percentage loss. Okay. So again, to summarize, for each episode, we'll reset the loss to 0, running loss to 0. Then we'll get the images and labels from the training set. Okay. Then we'll clear the old gradients before back propagation. Then we'll feed the images to the model to get the predictions. Okay. Then we will calculate the loss against the original labels from the training set. We will back propagate the loss. We will update the weights and we will update the running loss. And at the end of each episode, we will print the episode number and the percentage loss. Okay. So with that, we are done with the step 4, that is training the model. Now in step 5, we'll evaluate the model. Okay. So basically, we will test the model. So we'll have a variable called correct. So this will be the total number of correct predictions by the model. And then we'll have a total. Then we'll set the model to the evaluation mode. So model.eval. Now let's disable the gradient calculation. So torch dot nograd, and now we'll get the images from the test set. So test loader. Next, we will pass these images to the model. So we'll get outputs. So outputs model, and we'll pass the images. Okay. Now, so this line extracts the predicted class from the model's output by finding the class with the highest probability. Okay. So outputs are the model's raw predictions for each input image. Okay. So it has shape, the batch size, comma 10, where each row contains 10 values, one for each digit. Okay. So digits are between 0 to 9. So total 10. And torch.max method finds the maximum value and index along with the dimension 1. So basically this torch.max method returns values and indexes. So values are the highest probability for each image. Okay. And we don't need this. So that's why we discard this value. Okay. And these indexes, the indexes of the highest value, which corresponds to the predicted digit. Okay. So that is between 0 to 9. And we call it as a prediction. And what is this 1? The second argument 1 tells PyTorch to find the maximum along axis 1, meaning we search across the class scores for each image. So let's say, for example, these are the outputs, okay? 2.1, 0.3, 5.6, 1.2, and so on. Okay, so once we apply torch.max function, the prediction would be 2 because 5.6 is the highest value, okay? And its index is 0, 1, 2, okay? So here prediction would be 2. Now we will update the total. So total labels dot size 0. So labels, these are the actual labels, and size 0 returns the total number of samples in the batch. Okay. And now let's update the correct. These are the correct predictions. So we'll prediction labels dot sum dot item. And at the end, we will print the accuracy. So here we are training the model, and here we are testing the model. Okay. Now let's run this. Okay, so after episode 1, the loss is 0.37. Episode 2, the loss is 0.16. So we can see that the loss is going down. After episode 5, the loss is 0.09. Episode 8, the loss is down to 0.06. And after episode 10, the loss is 0.05. So after episode 10, the training has completed. And this accuracy is coming from the testing. So we have tested the model on the testing data set, and the accuracy is 96.57%. So that's good. So with that, we have completed the 5th step, that is evaluating the model. Next, we will build the Pygame. So this Pygame will allow user to draw a digit on the screen. Then we will take this drawing, process it, and pass it through the model, and model will make predictions about the number. Okay. So let's go back to the IDE and Pygame. So we'll start with a function called drawDigit. First, we'll initialize the Pygame. So pygame.init. Next, the window size. So that will be the size of Pygame window, 280. So this would be the 10x scale of 28x28. Next, we'll have the display height. So we have the extra space here for displaying the predictions. Now let's have the screen. So that is pygame.display.setMode, and we'll pass window size and display height. Let's add the caption as well. So display.setCaption and drawDigit. Clock pygame.time.clock. So we'll fill the screen with the black color, and let's have two variables. Drawing is set to false and prediction to none. Let's have the font for the drawing. So pygame.font and none 36. Now while true, first we'll clear the screen. Now let's handle the events. So event pygame dot event get. So let's understand this. So if event type is quit, we'll quit. And if event type is mouse button down, so that means when we start the drawing, so we'll set the drawing variable to true, and mouse button up, that means when we finish the drawing, so we'll set the drawing to false. And here we will call the function for the prediction. We'll implement that function in a moment. And if the event type is key down, that means if user presses C, we'll clear the screen and we'll set the prediction to none. Okay. So this is when a user actually drawing the digit on the screen. So event type is mouse motion. So that means mouse is in motion and the drawing is true. So drawing is true when mouse button is down, and when mouse button is up, the drawing is false. Okay. So this functions draw the circle and on the screen, and this is the color of the circle. So 255, 255, 255 RGB value. So this would be in white color. Event.pos. So this is the X comma Y position of the mouse when event occurs. Okay. And 8, the radius of the circles. So this controls the thickness of the drawing. Okay. So how it works? So when user moves the mouse, when holding down the button, circles are continuously drawn at the cursor's position, creating a handwritten digit effect. Okay. Now let's display the prediction. So if prediction is not none, let's create the text for the display. So we'll say font dot render. So this is the text we want to display on the screen when prediction is not none. So we'll display prediction text and predicted value. And this is RGB. So we will display the text in green color. And screen.blit function puts this text on the screen at this location. So this is X comma Y. Okay. Then we will call pygame.display.flip. So this updates the display to show the new content. Okay. And then clock.tick. This limits the game loop to 60 FPS. Okay. So now we are done with the draw digit method. Now let's move to the process the drawing. Okay. And this line extracts the RGB pixel values from the Pygame screen. The result is 3D NumPy array, and the shape is width, comma height, comma 3. Why 3? The number of channels, representing the red, green, and blue channels, RGB channels. Okay. Now this is the colored image, so we need to convert it to the grayscale. So this line applies the grayscale conversion formula, right? So 30% of red, 59% of green, and 11% of blue. Okay. And this results in 2D NumPy array where each pixel has a single intensity value instead of separate RGB values. Okay. So we'll not go much into the details of this because our objective is to learn AI. Now the image extracted from the Pygame may have different axis orientations compared to MNIST images. Okay. So we will apply this transpose function so that it will match with MNIST dataset orientation. Okay. Now we will have to resize the image. Okay. So remember the window size is 280 and the model is trained on 28 into 28. Okay. So we'll have to resize the image. So we'll use this function resize. So this interpolation is used to downscale the image while preserving the details. Okay. Now using the as type function, we'll convert the pixel values from 0 to 255 to 0 to 1. And then we'll normalize the value to -1 to 1. same as MNIST dataset. Okay, same like this. Then at the end, we'll convert it to PyTorch tensor using torch.tensor method. So here we'll convert the NumPy array to PyTorch tensor. Okay. Then we will add two extra dimensions. The first one adds a batch dimension and the second one for the channel dimension. Okay, so it would be something like this 1, 1, 28, 28. Okay, so this ensures the input shape matches what neural network expects. Okay, and then at the end, we'll return the pre-processed image tensor. And with that, we are done with this step, process the drawing. And now the last method is making predictions. So let's have a function. So we'll have function, let's call it as predict digit. And this will take screen, the game screen. Okay, so we have a method for making predictions and it takes the screen, the game screen, and we pass the game screen to the process drawing function and we receive the tensor. We check if it is done. And this part is pretty much same as the testing dataset part, this part. So here we'll set the model in the evaluation mode, then disable the gradients calculation and pass the image to the model and get the output. And using torch.max method, we'll get the prediction and we'll return the prediction. So we'll call this method here. So we'll call predict digit and we'll pass the screen. So with this, I believe we are done. So now we can run this code. Excited, right? So let's run this. Okay, so the training has started. Episode 2, the loss is 0.16. Episode 5, the loss is 9%, 8%, 7%, 6. Okay, so we are done. Accuracy is 97.05 on the testing set. Okay, it did not show the Pygame window. So let's check that. Okay, we missed one thing. We did not call this draw digit method. Now let's run this again. Okay, so we have the Pygame window. Let's draw. Okay, so we have an issue. Argument 1 must be Pygame surface, not tuple. So let's check that. Oh, so there is a mistake. Uh, Extra brackets. Now let's run this. Okay, so we have the Pygame window. Let's draw. Okay, something is wrong. Not able to draw. There's no prediction. Let's check that. Okay. Okay, so the first thing, we need to have the prediction value. And this should be outside of event loop. Okay. Now let's run it again. Okay, so we have a Pygame window. Okay, still not able to draw. At least we got the prediction. Let's check it again. Okay, I believe this is the issue. We are clearing the screen. We already have a key down event. If we press C, the screen will be cleared. So we don't need that. So let's remove it. Now let's run it again, and hopefully this time it would work. Okay, so we have the screen. Now let's draw. Okay, now we are able to draw. Okay, so the prediction is 1, so it's looking good. Let's clear the screen. We'll draw true. Okay, prediction is 2. Let's draw 3. The prediction is 3, so this is looking good. Let's draw 4, and prediction is 4. Let's draw 7. This is wrong. Okay, so this time it's right. Let's draw 5, and the prediction is 5. So again, correct prediction, this is 6. So we can say that this is pretty accurate. And that's it. We have successfully built an interactive digit recognition app using PyTorch and Pygame. Now you can draw any digit on the screen and our neural network will predict it in real time. So this was a simple implementation using ANN for small images, but in future videos, I'll take this further by using CNNs to handle more complex images with higher accuracy. If you have found this video helpful, do not forget to like, subscribe, and hit the bell icon for more exciting deep learning projects. Thanks for watching. I'll see you in the next one. Bye-bye.